Lesson 210, tables with decimals. In the previous lesson, we had an example of a bar graph that contains some values of gold medal long distance jumps in the Olympic Games. And we did some analysis of that data and answered some questions. In this lesson, we're going to be looking at data that is organized in the form of a table. This table has two columns, and so it's important first to understand the type of data that is contained in this table. On the left column, we have planets, and in the right column, we have each planet's orbital distance from the sun in AU. So AU is short for astronomical units. And looking at this teaching note and looking at the data, you can see that the standard unit of measure, or the AU, is all relative to how far the Earth is from the sun. In other words, if you think about how we measure distance, for the most part in feet, we know what a foot represents. And if you know what a foot represents, then you know, relatively speaking, what it means if something measures less than a foot, if something measures to be about 5 feet long, 10 feet long, and so on, because you have a sense of what a foot represents. Here, if we say that the distance from the sun to the Earth is 1 AU, 1 astronomical unit, well, the planets closer to the sun, Mercury and Venus, they're going to have a smaller orbital distance from the sun, meaning their value is going to be less than a whole, while the planets that are further from the sun than our planet Earth are going to have a value or an orbital distance greater than 1 AU. And here in particular, if you look at Neptune, Neptune is coming in at 30 and 1/10 AU. That means that Neptune, the farthest planet from the sun, sorry Pluto fans, is almost 30 times the distance from the sun as the Earth is. Moving on. Question 1 asks us to compute the distance between these two planets' orbits, Saturn and Mars. So if we look up, Saturn's distance from the sun is 9 5/10 AUs. Mars' distance from the sun is 1 5/10 AUs. And if we set that up as a subtraction problem, 9 5/10 minus 1 5/10, remember to line up these decimals by their place value. Insert the decimal point where it lies. 5 minus 5 is 0. 9 minus 1 is 8. We get 8 AU is the distance between those planets' orbits. And again, just for fun, I'm not sure that what I'm about to do is really necessary. It's just for fun. But if you visualize this, it would be something like this. We've got Mars with an M. We've got Saturn with an S. We are calculating the distance between their orbits. Moving on to question 2. Neptune and Uranus. Always the planet name, most fun to say and imagine how it's pronounced. Neptune is coming in at 30 and 1/10 AUs. Uranus is coming in at 19 and 2/10. Let's set that up as a subtraction problem, lining everything up by its place value, inserting the decimal point right where it lies. And begin. 1 minus 2, the 1 needs to borrow. Can't borrow from the 0 yet, so we need to borrow first from the 2. Then the 0 becomes a 10, and now this 10 has something that the 1 can borrow. 11 minus 2 is 9. 9 minus 9 is 0. 2 minus 1 is 1. We get an answer of 10 and 9/10 AUs. Jupiter and Venus. Okay, so let's start with Jupiter. According to the table, its distance from the sun is 5 2/10 AUs. Venus is coming in at 72 hundredths AUs. We're subtracting. Insert the decimal point right where it lies. Do you see where we can fill in a 0? And now we are ready to solve. 0 minus 2, can't do it yet. 0 needs to borrow. 10 minus 2 is 8. 1 minus 7, the 1 will need to borrow. 11 minus 7 is 4. 4 minus 0 is 4. We get 4 and 48 hundredths AU. Finally, Mercury and Earth. Earth, of course, has an orbital distance of 1 AU. Mercury, the closest planet to the sun, is coming in at 39 hundredths AU. Do you see where we can fill in a 0? Insert the decimal point right where it lies. We'll need to subtract across zeros here. Ten minus 9 is 1. 9 minus 3 is 6. 0 minus 0 is 0. We get 61 hundredths AUs.